Good morning, mathematicians. How we doing? How we doing? Finally put up a new video for the first time in a long time. Gonna try and make that happen more often. And yeah, on a regular basis. I need to try to keep office hours a little shorter. I really do. I'm sorry about that, but I do. Especially if I'm going to be making videos as well. That's so many hours in the day. I need to find a job. Okay, where are we here? I think we were talking about the Sylow theorems. And I realized yesterday I said that probably we would have to one should look at the class equation, but actually I don't think that's the best way to solve it. Right, I think the argument goes, someone had mentioned in chat actually as well, that if you take the what am I trying to say? Too early. Need more coffee. I think the point is, yeah, all of these Sylow subgroups are disjoint. So if you had 30, so if we had 30, well, not disjoint, but only intersect at the identity, right? So we had 30 groups of order 29. Well, then how many elements does that account for? Well, each of them have 28 non-identity elements that are all pairwise disjoint, and then plus the identity. So this should account for, oh my god, you're going to see finally exposed how bad I am at arithmetic. I honestly, I write the whole thing out like this every time. I go 2 times 3 plus 20 plus 3 times 8 is 24, add a 0, plus, oh, I guess that's it, right? 8 times 0, yeah. So, what's that, 321? And our total number of elements in the group was, I guess it was 29 times 30. That's true. I do need to read a course on arithmetic by Sarah. Very, very true, Boris. Very true. Which is what, 350? And so, good morning, Ken. Wow, you're so on the ball today. And so that leaves us with what? How many elements left over? That only leaves us with 29 elements left over. So, hello, Russ. Hello, Russ. Is this the best way to do it? Oh, I thought this works in other cases, but okay, let's see. This leaves us with 29 elements remaining, and those need to account for all of the elements of order 2, 3, and 5. Right, 2, 3, and 5. Hmm. No, does this approach still work? Because this works in other cases where you can't immediately. You always tell people you're a mathematician, not a calculator. Yeah, yeah. Um, True. Although I still feel like, I don't know, there's a part of me that's like, maybe I should just sit down and practice getting good at arithmetic. So when people who don't know anything are like, oh, what is this number times this number? I can just spit out the answer and then the book, whoa, that's crazy. um, as in, you think I need to go case by cases for the numbers of other Sylow groups, maybe? Oh, yes, right. That's true. Right, 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 right. Right, right, right. Right. So, if any one of these other Sylow groups, right? Because what was the original question? It was just to show that it has a normal subgroup of order 29, or just that it has a normal subgroup. Because one of the things you can say is, okay, if each of these groups, if there is only one of each of these groups, then um, then of course it would be normal by the Sylow theorems. So imagine each of these groups you had at least two elements. Um, so if each of these groups had at least two elements, you would have at least two non-identity elements coming from the two order two groups. We already counted the identity in here, by the way. You would have at least four, so there's two non-identity elements in each of these three things. So you'd have at least four elements. You'd have at least four elements in coming from that, and then finally you would have 2 times 4, at least 8 elements here. So that would account for. Oh, yeah, maybe this trick doesn't work. This trick works in another case because when you do this, you end up saying, "Oh, well, look, there's not enough room to have enough elements of the other orders." So maybe we do need to look at the class equation after all. Your go-to for normie conversations is always explaining Brouwer fixed point. You don't even like homotopy or algebraic topology that much. Yeah. Yeah, mine is to talk about symmetries. Just grab some physical object around me, and I'm like, oh yeah. And people are like, what are you doing? What are you working on? I'm like, oh, I'm trying to like classify kinds of symmetries. And then I just rotate some physical object by them, and they have some visual, and that's normally the end of the conversation. Yeah. Yeah. Wait, so what's going on here? What's going on? This is embarrassing. I should be able to solve this problem. Oh, oh boy. Um. Hmm. Interesting. Yeah, I wonder. Oh, I wonder. Maybe the key is to do Sylow on the other ones, right? Maybe the key is to do Sylow on the other ones, and then show that we have a certain number of Sylow groups in the other cases. Um, is that conceivable? What even is the missing, the other? I always forget the exact statement to Sylow 3. Divides M and is congruent to 1 mod P. Right. Divides M and P divides M and is congruent to 1 mod P. Oh, I lost chat. Right. So if we look at 2, then M would be 29 times 3 times 5. Does not divide that. Wait a second. Sorry. Okay. Right. So N2 rather has to divide 29 times 3 times 5. And it has to be congruent to 1 mod P. Okay, so in this case, all that tells us is that it's odd. So we know that it's odd, but it could be any one of these. It could be any one of these, but I guess we know at the minimum it's 3. No, wait, because it could also be 1. Tricky. Okay, but here's maybe how we combine the arguments, because but it can't. No, maybe it could be 1. Dang it, Bobby. That's my very terrible Hank Hill impression. N3 is 29. I should have thought about this before talking about it again on stream, so you guys would think I'm smart. N3, there's a 4th Sylow you always forget about, the normalizer of P. Oh, maybe that comes in handy here. Let's see. Let's just see. Okay, so it can't be 2. It can't be 5. It could be 10. Could be 1. It could be 10. It could be 29. How many times? What's 29 mod 3? 27 plus 2, so it couldn't be 29. Did I already use that part of Sylow 29? Yes. So we got that part of Sylow 29 to get. We know that there is either one Sylow subgroup of order 29 or 30. And we're trying to prove that there can't be 30. And so then I also use the fact that, well, if there's 30 subgroups of order 29, then it accounts for this number of elements. Maybe I made a arithmetic mistake. I don't think so, though. And then I said, okay, well then that's all of the elements of order. Wait, did I make a mistake here? No, that's true. So there's 321 elements of order 29. But it has to divide 15? Wait, what has to divide 15? The number? Thanks, Dason. Yeah, maybe, I don't know. Maybe there will be a collab in the future. I don't know. I don't know what we'd collab on exactly. Probably something to do with Galois representations. Yeah, I don't know. That's okay. That's okay, Jose. I'm exposing how bad I am at basic arithmetic as well today. So, yeah. Wait, are we sure about this? Yeah. Okay, so where are we here? Right. So we're trying to rule out the case that it's 30. So I want to somehow say that it's problematic that the other that we would have 29 elements of some order. Yeah, I think the current approach I'm on is not the right approach, but here we are. So this is just easier if I write all of this mod 3, right? So mod 3, this is 2, 2, and 2. These are all 2. So the product of any two of them, it could be, right? So it could be, isn't 29 prime? 29 is prime. Yes. What? 18, 27. 27 is 0. 28 is 1. 29 is 2. Yeah, no, this is right. This is right. You're scaring me, Boris. So this could be 1, this could be 10, this could be... Yeah, I feel like this approach maybe isn't helpful. But let's keep on it. So this is 58. What's the question? I thought you were counting groups of order 29. Yeah, we're counting the Sylow subgroups of order 29. Maybe we do need to go to the class equation. Do some conjugacy class business. Maybe yeah, see, I looked at this last night actually before I went to bed. This is some of my bedtime reading. I did some complex analysis bedtime reading, did some group theory bedtime reading. Oh, right. That's because I see. I see. That's because he's just showing there's a normal subgroup. Oh, let's look. There's some other proof methods here. Don't I get pissed off when it takes this long to prove something simple like counting Sylow? You always feel like shit when you have to prove some group theory result and it takes you this long. I mean, I do feel embarrassed that I'm, I've literally instructed a course on Sylow, and here I am not solving this problem instantly. And so I don't know. It's more, yeah. But no, I wouldn't say I feel aggravated in any sense. If anything, the real detriment to my well-being as a consequence of this is the fact that I'll probably not put this problem down until I solve it. Um, no, I'm going to try to be a good boy. I'm going to try to be a good boy. I'm going to try to end office hours at 9. I'm going to stop thinking about this problem and until bedtime. I'll think about it before bed. If the answer hasn't revealed itself to me at some other point during the day. Yeah. Yeah. Okay, let's see. Let's take a look at this approach. There are no simple groups of order 24. I mean, this isn't going to be helpful for us, but indeed, let G be a group of order 24 and consider its 2 Sylow subgroups. It's either 1 or 3 such groups. If there is 1, it's normal and it's not simple. Yada yada yada. Okay. Why do we study integration over LCH groups? LCA groups, do you mean? You understand the subject and its goal, but you don't know where to start. Well, what's a good way to sell this idea? I mean, okay, so I mean, the idea is we like groups, right? Locally compact Hausdorff. Oh, okay, I'm not used to such luxuries as assuming Hausdorffness. So, we'll take it as given that we like groups. We think groups are interesting. We want to study groups. We're trying to classify groups. Of course, the point of the new series I just started is that, I feel we send this message like, oh, the classification of finite simple groups is a wonderful big thing. It is, but like the more important thing is how you put groups back together, right? If you went to a mechanic and they're like, oh, I took your car apart into so many pieces that I can't take it apart into any smaller pieces. I broke it down to its indivisible constituents. You go, oh, cool. So you put it back, right? You found the problem and you put it back, right? He's like, hey man, it took me 10,000 hours of work to break your car apart, right? You wouldn't be very impressed, right? So we want to put groups back together. But okay, my little rant aside, let's consider finite groups done and uninteresting. So we move on to new kinds of groups. Infinite groups. Well, there's a lot of infinite groups, and there's some really crazy infinite groups that you can cook up. If you accept large cardinals, you could cook up groups that are outside of ZFC and whatever. So you want to cut things down a little bit. And we are just inherently very visual, very geometric creatures. So naturally, one would want to gravitate towards groups which have some sort of geometric structure to them, right? So hence, we come to topological groups. Or to I've never really studied the Thompson's groups in detail, or many of the finite simple groups. I should someday. Topological groups, Lie groups, algebraic groups, and so on, etc. right? Of course, these are special cases of this one. So some sort of groups where we have some sort of extra structure, right? If you have extra structure, I mean, then it's just nicer to work with, right? A cool one, infinite one, is P group with trivial center. Proof that God hates us. Boris, if I make a video on that, I'll make that the thumbnail. Proof that God hates us. Actually, that gives me a good idea for a video. Just like all the ugliest theorems in math. Maybe I should like go to Reddit and crowdsource like the ugliest results, and then just make a video called "Proof That God Hates Us," listing all the results. So okay, topological groups, Lie groups, right? So we have all these topological groups, right? And that just makes life easier because there's a group plus some other compatible structure, so it just gives us a little bit more to hold on to. Than just, I'm studying an abstract infinite group, right? The math is way too abstract for you as a physicist undergrad. Well, I am talking very abstractly at the moment as well. I mean, I do talk about very abstract math, but I'm also talking abstractly about math. By the way, physicist undergrad, you might find this math too. There's me in the past. You might find this math too. What was this? What was this channel? There's a new channel I just saw. Dang it! I don't remember what the video was called, but. Yeah, look, Richard Beale. There's this amazing series of videos. I was watching it a little bit this morning on gauge theory and stuff like that. Also, then I was led to. I haven't really watched much of it yet, but explaining physics. Dirac equation. There was a really cool explanation of the Dirac equation in this video here. So just a shout out of cool things. Zvi Rosen has best Sylow theorems on video. Not if I have anything to say about it. I'll have to go. Yeah. Yeah. Well, you're just interested in pure math, so you watch my content just to learn new, interesting stuff, even though you don't understand. Well, that is cool. I was not proving stuff. But okay. Anyways, come on. I gotta stay focused. We gotta end office hours soon. So, right. So it's just if you have structure there, like for example, like we love studying vector spaces. Vector spaces are great, right? But what's even better than a vector space equipped with some sort of inner product, right? Like a Hilbert space or something. It's just more structure. There's just more you can say about it. There's just more you can do with it. So again, as we go up in layers of structure, it's just easier to study these infinite groups because there's more things you can say on it, right? And so certainly Hausdorffness, that's not normally an assumption I see, but Hausdorff, yes, the Heisenberg group does have something to do with encoding momentum and position. That's something I should cover at some point. But Hausdorffness is a pretty benign assumption. Where things maybe get interesting is local compactness, right? Why do we care about local compactness? And the point is, again, so local compactness, as you know, implies the existence of a Haar measure, a sort of God-given measure. He might hate us, but not so much that he doesn't want us to be unable to do calculus on groups. And so, what reference can you learn algebraic groups without schemes? You should just learn it with schemes, bro. You should just learn it with schemes. You should just learn it with schemes, bro. You should just learn it with schemes. Getz and Han. Go look at Getz and Han. Springer talks about it in terms of varieties. Springer's linear algebraic groups talks about it in terms of varieties. So, yeah, you could go there. That's a classic reference. Maybe Humphreys as well, actually. Also Humphreys. But he focuses more, I think, on the Lie algebras and root systems. So, I mean, again, here we go. It's just there's a certain class of groups that, again, you could study abstract, random abstract. Springer is a real person, yeah. Random abstract infinite groups. He's a very busy man. He's a Stephen King of math. Yeah, he wrote every book that's a Springer textbook. And it's like, well, we got to study some class of groups, you know. It's like, oh, I want to study some structure. Oh, this vector space has an inner product. Why don't I study what the hell I can do with that? That seems like a powerful thing. Oh, look at these groups. These groups have a God-given measure that just comes with the topological group. Okay, well, I mean, probably I should study that. Probably I should look at that. And so, I mean, that's just easier to get a grip on. It's just more structure, right? An abstract group is very slippery. You can't hang on to it, right? You know, you got this hard measure, grab onto the hard measure and cling on to it with all your life, right? So, yeah, that's the basic idea, is that if you got a hard measure, now you can do integration, and probably that means something, right? Probably there's something interesting to say there. It's just more structure to actually study and say something about. And the other reason to be like very, very excited about this prospect is, for example, if you want to study, let's say we're studying the additive group of the real numbers, we have the very powerful notion of Fourier theory, right? And so, like the Fourier theory, people think it's analysis. It's actually just a statement in representation theory, right? It basically just says that the L2 space, it basically just says that this representation breaks up as a direct sum. The L2 space of this quotient breaks up as a direct sum of a bunch of irreducible, I mean, a Hilbert space direct sum of a bunch of irreducible representations. It also says that there's, if you take the trivial, you look at R modulo the trivial group, there's also a way of taking like an integral of spaces, and it basically tells you how this representation breaks up as a sort of like integral of representations, which now depend on like a continuous parameter. And I mean the whole thing, and then the whole thing is like, well, I mean, representation theory, again, come back to this idea of, okay, we want to study groups, infinite groups. There's not a lot of structure there. How do I understand a group? Well, representations. I can use representations to try and understand a group. If I have some representation of a group, then there's just more things to understand. So, wow, if I have access, you know, so you look at this and you say, okay, Fourier theory, you're absolutely right, Boris, it does sound like that. Fourier theory now gives me access to understanding the representation theory of the additive group of real numbers. So maybe having access to Fourier theory on a group will help me understand the representations of a more abstract group. Okay, so that's just a little bit of a pitch. I don't know if that was convincing, but that's a little bit of a pitch as to why you would consider locally compact groups. I mean, Hausdorff is whatever. This is just some extra niceness condition. The local compactness is what gives you the result about the measure. Yeah. Still don't understand Haar measure, but it's very ubiquitous. The Haar measure is just you have a God-given measure with nice properties. The ordinary Lebesgue measure on the Rn viewed as an additive group is slash the Haar measure, just up to scaling. So that's your main example. There's some really cool examples in Dietmar's book where you can do computations by just, you don't even need to know so explicitly what it is. Like you can basically, like for example, in I think QP cross, you basically just say, well, I'm going to take the Haar measure. Well, there's a way to relate the additive Haar measure on QP plus to the multiplicative Haar measure on QP cross. And then you say, I'm going to normalize the additive Haar measure so that ZP has volume 1. And then basically just using this fact alone, so you don't need to know anything else about how it works on other sets, and using some facts about that, like ZP mod, the ideal generated by P is isomorphic to the integers mod P, you can then prove that like the integral, what is it? It's something like the integral of the p-adic absolute value to the power s over over QP cross is like the pth factor of the Riemann zeta function or something like this. And then like this is an important step to like Tate's thesis type things, and proving all of these interesting things about zeta functions. Okay, we're going off the deep end. It's after 9. I need to go. Do I have any experience with representation theory and character theory? A little bit. You're doing research right now trying to prove relation between orthogonal basis groups and GVZ groups. I'm not familiar with those. All that comes with an L2 action? Yes, it's just the translation action. It's just the translation action, right? It's just the translation, like x dot f at y is x plus y. It's just the translation action. Yeah, sorry, Will, I can't help you with that question. I'm not familiar with that area. Can I explain the integral thingy here? I'm guessing you meant here. I will do that possibly tomorrow. I will do that possibly tomorrow. Does local compactness have an equivalence in algebra? I don't know. Yeah, sorry, Nerd Coke. That's the way it goes. I did about his videos of completions of Q. No, but I was thinking about making my own video about Ostrowski, so I don't know. I don't know. Anywho, yeah, I'm gonna go do some work. So I'm gonna prove some things. You go prove some things.